very much. I'm always surprised when somebody introduces me and starts reading all this, and I wonder who gave all these things, Anyway, it's a great pleasure to come here and see such a fantastic group of mostly students, informal, interested, I think. I don't know whether you will be interested at the end of the talk, but at least at this time you are all very interested looking. I have to tell you give you a little apology. I was out of the country and I came back last Friday from Hong Kong. And this morning I was told that I was supposed to come here this evening. So I had to quickly look up what am I going to talk about. And I picked up some slides and made up a sort of an informal presentation for tonight. So if it's not very structured, in your opinion, I hope you will forgive my situation. But I'll try to make certain points that I think quite relevant today, and probably was relevant since architects had to depend on engineers for certain of their structures. As it was mentioned, it just happened that, in fact, I am the only engineering partner of a huge architectural firm with more than 20 partners. Now, this is an interesting thing because it shows from a basic relationship what is the scene in terms of the kind of joint working habits of the architects and the engineers. And you go back to the school and you find about the same. I hope it's not that bad here. But in many schools, even now, the architectural students work in their own world, and the engineering students work in their own world. The architect is generally I'm saying, please don't think that's the final statement, generally slightly on the side of being an extrovert, have great ideas about creating things, turning the world around, and therefore he's always looking for creative solutions that may or may not stand. That's not altogether very relevant sometimes. Whereas the engineering student who go to the engineering school are also very good students, but they're generally on the introvert side, and they're very happy most of the time juggling and playing with numbers, with different mathematical formulas, coming down with different differential equations, and coming up with glorious mathematical solutions. And as a result, what happens, and of course the engineering education quite often, unfortunately, never stresses the need to question the type of solutions. Most of the time, the education stresses the need to find a solution, no matter how you get it mathematically, as long as the solution is right at the end. So what happens is when in the real life, the architect from your school, you come out, you have the great idea of creating fantastic solutions of spaces and forms. And the engineer comes out, also a very bright boy, comes out, and he has great need and interest to simply solve 1 million simultaneous equation. So what happens is that when the architect and the engineer are put side by side, the architect looks at a program. Let's say he has to design a school or an office or a hotel or whatever, and he comes up with a grand idea of a building. Quite often he also thinks, rightly or wrongly, that it's also a grand structure. And the engineer quite often, instead of asking whether this really makes sense or not, is very happy because the thing looks so complicated, he can really use the latest techniques to solve them. And this relationship, unfortunately, results in rather tragic buildings, because in the opinion of the architect, it was a great structure sometimes, but in reality, it may quite often be a very tortuous solution of an otherwise possible simple solution. The engineer, on the other hand, remains oblivious of all this, and he has solved his million simultaneous equations, and he has gone home and said what a great day it was. But I think in the end, the architecture of the society suffers. And I think if you look around, you would see in many, many areas of buildings, and I'm talking about buildings, not bridges, where architects generally don't play too much of a role, but in buildings you'd find grand expressions, quite often supposed to be structural expressions. And if you analyze it, you'd find it's the most tortuous way to do a simple thing. And I think if the engineer and the architect worked a little closer, where the engineer felt a little bit like an architect and the architect felt a little bit like an engineer, I think together they could certainly create a much more direct and yet interesting and exciting building. And I think it has also another point, because as you know, engineering is related much more than architecture to an economic solution. An economy is not just a personal thing. If a building is economical and yet beautiful, then at the end the society has spent less money and would have that extra money to spend on something else. If the building is a monumental all the time and spending millions of dollars, then somebody at the end is spending all the money on that building, and there's simply not enough to go around for other many important buildings and projects of the society. And I get very interested in that too, because an expensive building may be beautiful, but by itself cannot be justified because it's expensive. In fact, it's a negative thing when a building is expensive more than it had to be, because somewhere along the line that money could have been used for some other purposes that society very badly needs. And we know in our society here, all over the world, and I say the same kind of a thing, architecture tends to go into monuments, and monuments are not always very good for the overall society. Few good, but not the whole city full of monuments. Well, with that introduction, I would come to the main subject, and that is, how does Skidmore, Owings, and Merrill work in terms of the engineer and the architect? When I joined SOM in 1955, I really came into almost the same kind of an environment. The environment was that there was an engineering department, mechanical engineering, electrical engineering, a structural engineering, and each one had a very good title, like the chief engineer. But all the partners and associate partners were all architects. It was kind of an interesting way to, I guess, solve this problem of departments. But as a result, most of the time when I was just beginning, every engineer thought the decisions have already been made. It's made by the partner or an associate partner somewhere, and it's too late to even talk about it. Let's solve the problem, get the beam size, get the column size, somehow make it work, and that's good enough. And I think in some small way, I think I have been able to change that. We have now a different approach, different attitude, and we hardly ever look at a project a priori with an a priori concept. We generally, at the very beginning, sit down, look at the basic program of the building, the architectural programming of the building. For instance, how many apartments, how many offices, how many hotel rooms, and that kind of a thing. And out of that evolved a building proportion, volume, space, kind of in a joint way, which has the structural and architectural input at the same time. And I think because of that reason, most of our buildings respond to the economic questions. And I think at the end, they probably are more, if I may use the term, rational. Now, you might obviously question whether buildings have to be rational. But I think in a small way, if they are rational, chances are that they're going to be rational also tomorrow. But if they're fashionable, tomorrow they may not be worth anything. So we have made some changes, and I think talking to different universities, I find the same kind of an interest is now developing in different universities. And most of the universities are now going into coordinated joint work between the architectural students and the structural students, so that they have an early communication developed before they get out of school. They have a respect for each other. At the same time, I think the realization of the limits of contribution by each one of the team. Now, I thought we should have a series of free questions and answers to make it more lively. But I thought I show you some slides which could, in a very quick way, give you an idea what is the contribution, if at all, of engineering, the structural engineering part of it in architecture as we have gone through in the recent years. And in some way, start with an introduction of what kind of a building or what kind of structures were built only a few years back or 100 years back, and what kind of buildings that are being built now. And in spite of all that is happening, what kind of interestingly unreasonable buildings are still being built. So I'll try to take you through that in a very informal way, and then we'll try to have some questions and answers. Let's see. Now, that slide is way up there. You know, this light is strong, I must say. The point here was really a humorous point. And if you look closely, you will see that coordination of all kinds are really needed to make a building. In this case, of course, the obvious situation is rather tragic, but if it would continue on larger projects, you can see it would be catastrophic. Of course, you know, here it was solved very quickly by using of a mover to bring the stairs up at the right place. Now, if we look at a city like Chicago, and I assume most of you have been to Chicago, in the last few years, the entire skyline has changed. The skyline, all of the taller buildings, now I'm not yet saying that tall buildings are any good, but I'm saying all of the buildings that you see, most of them are built over the last 15 years. And what is happening is there's a tremendous redevelopment of the whole city as a whole, and as a result, we are seeing a lot of very interesting forms, both structural and combination structural architectural, that are coming up on the skyline. Now, this, in fact, has been possible, and I'll show you a few more slides later on, has been only possible because valid structural solutions have been incorporated into overall architectural solution. That is, the structural solution and the architectural solution, in fact, blended together to come up with the final total building solution, and that they were not separate. They were not an a priori architectural concept and somehow solved by structural analysis. Now, going back only a few hundred years back, a building, this one is the Cathedral at York, This is all taken by myself, so they're not the high quality slides, but you can see the point is there's a very interesting architectural structural blending. Maybe there are certain redundancies still in fact remaining in the form of the vault, but there is a definite flow of load that required the overall shape of the vault. And the material used at that time just could not span that kind of a span in any other way but to go through some kind of an arch action. But here, as you know, at that time, there wasn't so much of a distinction between an architect and an engineer. The same man who was the builder, constructor, engineer, architect, sometimes the same man. The same man went around and supervised the entire construction. At the same time, he designed the vault, the proportions, and he took the responsibility for their stability as well. So it really was one man master builder. Now, if we look at the inside of it and we see the details of some of the interior walls, we find the same kind of a very delicate construction. And I'm looking again at the structural point of view, and I would say that today, if we wanted to do that in reinforced concrete or steel or whatever material, we probably would have a number of structural engineers analyzing those columns and a number of architects looking at the proportion and see whether it makes sense. And yet at that time it was the same man basically who took care of the stability, the strength, and at the same time decided on its proportion and its aesthetic values. Now we look at early engineers now who really came up different from the architect or the builder, the master builder. And Brunel was a good example because he really not only built bridges, but he built buildings, and he built even a boat, a huge warship. And I think it shows that they're again completely unattached or unaffected by any other basic aesthetic judgment. Brunel's solution of this bridge, unfortunately I don't have the other slide that shows the whole bridge, but it's a very early suspension type bridge using I-bars. And this bridge really fits so beautifully in the environment, as well as it spans so beautifully over the gorge, that I would say that it was truly a masterpiece in bridge aesthetics. And yet, it was really again one single man who designed the structure and decided on the proportions, which obviously had strong aesthetic values even in his mind at that time. And now we come to the 20th century, the beginning of the 20th century, when clearly we find a distinction developing, very strong distinction developing between the architect and the engineer and their practice and the product. The example here, as you see, is the Merchandise Mart, a building that in reality I think is somewhat of a non-entity, but in terms of architecture, but in terms of a mass, it certainly is one of the world's biggest building. Something in the order of 4 million square feet right in one building. Now that's a huge space in one building, and yet if you look at the basic proportion and all that, it's a solid building, and you have no idea where the columns are. And you also don't know whether it's really a bearing wall structure, or it's really a steel structure, or it's a combination of both, or what. But this is an example where the architecture and engineering in some way were truly separated. And I personally feel that if there were more concern for the expression or the clarity of the structure which the Chicago School of Architecture had developed, the building would have looked certainly much more interesting and exciting. Now, on the other hand, if we look at a building, it's not a very good slide, but if we look at a building like the Monadnock building, which was built in 1889 and was one of the earliest bearing wall construction, and in fact, even today is one of the tallest bearing wall type construction in the world. Not the tallest, but it's very close. We really see in the details, and if you walk around the building, very beautifully done, because the structure, in fact, was also basic expression of the architecture. And except for a few things like the decision to clarify or clearly show the Chicago type of fenestration, I think the building represents the philosophy of the Chicago School of Architecture that really started on the principle of the simplicity of structure as a basic element in the architectural expression. Now, at that point, we should probably discuss one thing, and that is architecture, after all, constantly deals with proportions. Proportions of beams, proportions of columns, and proportions of arches and all that. And you know, it's an interesting thing that today we build buildings like this. The United Airlines Administrative Center building in near the O'Hare Airport. This building is post-tensioned, two-way slab, a waffle slab, and it spans 66 feet in one direction and 60 feet in another direction, and has no columns in between. And it really is a very, very slender-looking slab. If you look at it flat, this is, of course, you're looking at an angle, so the span looks smaller, but if you look at a right angle, it looks very thin. And one would say, in today's architectural form, it says it really is a very beautiful structural expression, kind of an architecture of today. And yet, if we had the same proportion drawn by an architectural student 300 years back, no matter which architectural school you are talking about, he would probably be thrown out right away, because he would be said you have no idea what proportions should be, and you have therefore no business in being an architect. Because at that time, 300 years back, there was no post-tension concrete, and there was no high-strength steel, and therefore somebody drawing that proportion would simply violate the basic materials and the basic technology of that time. And therefore, it would be a priori assumed that that proportion is not valid, and therefore the architectural student didn't know what he was doing. It's an interesting point, because if we look at architecture, which is really very much dependent on the material and technology, the proportions of the building are very much the function of the technology and the material, and really not that many a priori things that you can go into. And that is a very important thing we find out. For instance, what is good in 1930 simply does not have to be good in 1970, because new materials, new technology has made other proportions equally valid and probably more relevant. Therefore, to hang on to the idea of 1930 and keep on drawing the same form would be completely erroneous and out of date. And I'm just giving an example, because this happened in every so-called school of thought in architecture, that the masters pass on to the disciple the proportions that they learned from their masters, except that in those years, those proportions have lost their meaning and sense because of drastic changes in the materials and the technology. It's the same way about arch. A lot of people like arch like anything. Arch was not, as you know, devised for steel, nor was it devised so much for concrete. It was devised for some materials like blocks, stone blocks, then masonry blocks, which could not in any other way be used to span a reasonably sized span. So if today somehow we put artificial arch, I would have to use the term, I would say that's an a priori decision that violates today's technology and the materials. And I'm sure there are forms that are probably worthwhile. They have certain visual values, but then probably we should use them where they're really valid, not use them just because you like the arch and you put arches all over. You know, that's my personal thought. Now I wanted to show you because of that, because this Today, we find all kinds of buildings with such very thin, simple lines drawn, and that makes a beautiful contemporary building. But the same proportion drawn 300 years back would be completely unacceptable, and the teacher would have thrown out the student immediately. It's the same way, another example of a building, the Empire Project, where you see again the very thin proportions. And these proportions are quite valid in terms of the materials. But obviously, again, 50 years from now, if somebody tries to copy that, that would be completely wrong, because there'll be other possible forms that probably would be much more relevant at that time. Now, we go into the longer spans. It's the same way what happened. What was considered a few hundred years back or about 1,000 years back, what was considered 80 feet as a long, long span for a dome to span. Today we span easily 400, 500, 600, and have stretched up to 700 feet. One Today we span easily 400, 500, 600, and have stretched up to 700 feet. One single soup of a dome or a suspended structure that would span that much. Therefore, its proportion and its forms do not have to reflect the forms of Taj Mahal or the St. Peter's. Its forms and proportions, therefore, should reflect its materials and its technology and simply be expressed. Now, I'm saying again, from the simplest structural way of looking at it, the point is to, at that point, begin the interaction between structure and architecture. For instance, also an insight, this is an arena in Philadelphia. Inside trusses, interesting forms develop simply out of the need rather than an a priori concept. We wanted to create an efficient economic span, and it turned out that the economic trusses became kind of inverse bowstring, like a suspended shape. And it turned out very pleasing. In fact, it was also much more advantageous for the people who sit up there and look down, so the trusses don't hit them anymore, they just go up that way. Now there again, a rational approach seemed to fit quite well with the remaining rational things like the line of sight and the general view of the arena inside. Now, today, of course, we can think of high-strength cable structures, and we're just building a building for the one of their research labs, and here you can see the roof is 150 feet by 300 feet, and it's supported on 2 columns. Now, obviously, if you tell someone, I want a roof 150 feet by 300 feet, and I really would like to see the roof supported on 2 columns, except that I really like a very clean straight line and the roof sitting on those 2 columns. Now that I would consider an a priori concept of how the roof should be. The roof should be the way the columns can support the roof. In this case, you take the column up and in fact hang it back from those cables, which are then attached at different points of the roof. So the concept of a 2-column supported roof would be completely ridiculous and I think fantastically expensive if somebody wanted the columns to simply terminate at the point of the roof. But if you accept the technological answer and simply carry the columns up and have the cables come down or some way supported, then the roof structure makes economic and technological sense, and I think it creates its own aesthetic value of the time. Now, this brings in the question of the influence of the recent technological breakthroughs in other areas. And it is the reason I'm showing you is just to show you the contrast, or not contrast, maybe the balance between a system of pure structure, as Bucky Fuller's dome in the background. This is in the Montreal Expo. And you see the spaceship, which is hanging right in front. Now, the structure in the back is a system by itself only, that is, system of the structure. The spaceship in the front is a system in the broader sense of the word, that is, where different elements, different materials, different technologies have combined to respond to an overall requirement. Now, in this case, the requirement was to send a man to moon. Beyond that, there was no a priori concept. Nobody said, look, I want a concrete-looking little ship. Or nobody said, I would like to see a little steel beam sticking out because aesthetically, I think I'd like that moon to have that kind of a structure. Now, in this case, the solution was strictly a direct step-by-step synthesis of a series of given requirements. And out of that, many, many materials and many, many technologies were tried. And the result was this spaceship, which has something like 15,000 subcontracts of different kind of things that have to go into it. Now, the lesson or the parallel we learned in the building industry, which brings the architects and engineers together again, is to realize that the a priori concept of a building, all concrete or all steel or all glass, may not necessarily always be true. We should really look at probably what is the building supposed to do. And if the building is supposed to do something, the answer may very well be a little bit of concrete and a little bit of steel and a little bit of aluminum might be a better solution, and in fact more rational solution, than forcing the entire building to one material or one type of a system. Now, this is only a question that could be raised from this, and I think I'll try to show you a couple of interesting solutions that in fact responded to similar kind of questions raised in building industry. Now, using this kind of a systems approach, I don't want to show you too many charts. This is one of the few, I think. You would see that there are variables which we call the design factors, and these design factors you can vary between technical and environmental. And you can see a whole series of design factors in technical are listed, and a whole series of design factors environmental are listed. Now, if you look at these two, you'd find right away that the idea of an optimum or a simple design is really to find a solution that responds to the factors that are listed in the most optimum way. That is, as many of these factors resolved nicely in the final building that we can possibly do. Now, there are many buildings which are started with an arbitrary a priori concept, and therefore, quite often, if you had this chart, you'd say, well, 70% of these factors really did not matter or were not used because the building started with the a priori concept of my aesthetics, and the aesthetics was the controlling factor, and the others had to just sacrifice. And my question here is that if you respond to these factors and respond to the technology, then maybe some interesting different forms of aesthetics would emerge, that you will not have to start with an a priori aesthetic, but the aesthetics will be the byproduct sometimes of trying to resolve all of these beautifully. And it's a very interesting process. It's kind of a synthesis process rather than an a priori starting point. Now, out of that, a couple of interesting examples. One of the things that the systems says is that we should try to use the same element more than in one way. That is, if there is a column, can we use it for a mullion? If there is a ceiling, can we use it for, if there is a floor slab, can we use it for a ceiling? If there is let's say, a mechanical system, can we use it also for lighting? That kind of questions that come in. That is, can we use the same element for more than one purpose? Do we have to build a building that is, let's say, all steel, and then cover it up with heavy concrete cladding, which looks like a separate structure, and yet it is hanging there free? Do we really have to do that? Why couldn't we build it that way so that it would look like a concrete building and it would be supported by itself? Or if we design a steel building, why couldn't you do it so that the steel also supports directly the glass and not have another concrete panel sitting on it? This is the kind of a question that sometimes lead to, in my opinion, if I may use the term, purer solutions to the basic problem, rather than slapping one solution over to the other and having a series of laminated buildings, which we find all the time. If you look around, you'll find the buildings going up, and then huge panels of concrete is sitting on them, which could almost carry the building by themselves, except that in this case, they are being supported by the steel frame. Now, so we looked at that, and early in the 1960s, 61 in fact, we looked at this and we said we really got to start doing this kind of building where the structure is also the supporting element of the window wall system. And the first time we used that was on Brunswick building, where the concrete columns became the mullion, and a jacket, as you see there, not jacket, the gasket, the neoprene gasket would simply accept the window wall, the glass, and therefore there was no need for additional curtain wall hanging around it. So Brunswick building really was in some way a very interesting approach to using the structure as at the same time an architectural expression in terms of the mullion as well as the spaces between those structural elements. The glass line in this case was moved about 18 inches inside, and as a result, I think this is not a very good picture, I must say, but it's really for early 1960s, it's really one of the first buildings that was totally structurally oriented, and yet the architectural expression came out of it and not as a separate element added to it. As you can see, the same concept then we have refined and used it in many other buildings, where the window wall system, as you see the column, becomes the mullion and supports the glass directly through a gasket type detail. And this is in One Shell Plaza in Houston. As you can see here, the glass fits right in between, and all those mullion type structure is in fact the real structure and supports the building and supports it against the hurricane wind, which blows there about 140 to 160 miles per hour in Houston. And because of the structural system that we developed, it was also very economical building. I mean, there was almost no premium for the height. And yet, I think it has a very strong, I would say, presence in Houston. If you walk around, I think this building has a very distinctive presence, where there are many buildings, I'm sure, just didn't make it. Now, there's another example of using the same element for more than one purpose. Now, here is the American Republic building in Des Moines, Iowa, where, and there are a couple of other buildings we have done that, where the mechanical duct, as you see here, which fits in between the architectural or precast, pre-stressed T, double T or channel type floor slab. The mechanical duct fits right in there. It circulates air. It also is used as the lighting fixture, so that we have the light, the air, the input and output, as well as the light, all in one element. And it fits in between the structure and completely eliminates the need for a false ceiling. Now, as we said, from the space research, the idea of mixing materials, we've gone beyond, and in some buildings we found that to have a steel building inside and then wrap the whole building with a concrete grid tube, closely spaced column, could in fact have the both advantages of a concrete building and the steel building all wrapped in one, and responds to the hot climatic condition in terms of heating and ventilation. So in Houston and in New Orleans, we have built two of these major buildings using the composite system, and we in fact modified it slightly and used one in Chicago. The Union Station new building is using this concept. The steel goes up very light. You see, a lot of people called me, they said, it looks unstable, it's going to fall down or what. But the idea was that the concrete simply climbs behind it and grabs the steel and makes it into reinforcement. And so it's a very interesting two-stage construction. There again, using the same, mixing the materials and taking the advantage of both to create again a new form of the building expression. This is just to show you what happened is that, as you see here, inside is really like a steel building with the columns and the beams and the floor slab. And the outside is the concrete tube, closely spaced column tube that grows and follows the steel construction. And because of that also, by the way, just a pure statistics, the building could go 2.5 to 3 days a floor, which is really quite fast. This is the finished building in New Orleans, which is 51 stories high, which uses that composite concept. Now, tall building is something that I have to give you my thoughts a little bit, because this is something particularly architectural students and the profession quite often misinterprets, I think, and says that tall building is just pollution of the skyline, and it's a bad thing and it is ruining the cities. And of course, unfortunately, many of the tall buildings have created the high-rise slums and the sociological problems. But I would have to say that the fault there again of those ills that have come up, like the high-rise slums of Chicago, is not the fault of the building. It was the fault of the program and the fault in terms of relating the development to the overall social and economic needs of the people who are going to live in there. And unfortunately, since we have not solved those problems, the buildings get the bad name of having the crime and all the problems. So that's the one side. And I hope that we don't simply go ahead and design buildings and house people, that we think before design those buildings how to really take account of all the needs of that society and not just the housing need, because housing need by itself can only cause from a low-rise slum to a high-rise slum. But we talk about the other urban area, the areas where we have other offices and apartments that are otherwise expensive and in the urban centers, and we look around and walk on the Park Avenue at 10:30 or 11 in the morning, and we find nothing but darkness. And we look around, we see the result is mostly because of the early development of buildings, which were built 20 to 30 stories high, absolutely end of the street to end of the street, filling up the entire site all the way up, so that it was really what has created the American scene of the canyons, as they say, the glass canyons and the stone canyons. But nevertheless, they're canyons because there's no space in between, and the sun doesn't get a chance to shine except between maybe 12 to 2, and there's hardly any wind that you have the feeling of fresh wind, because there's hardly any gap between the buildings like the street. And I think in response to this kind of a problem, where the society has already accepted, politically, economically, accepted the high density of population in the cities, the alternate solution to create an environment may in fact be to go taller building. The same 4 million square feet, instead of being built in a 50-story building, build it in a 75 or 80-story building, but leave a lot of ground space open, leave a lot of people's activity, leave a lot of space between buildings so that the sun can shine and wind can blow, and people on the ground level do not get completely overpowered by this feeling of canyon. Now, this is at least my hypothesis, and I think my justification, as far as I can see, in really trying to help develop a series of recent tall building systems. Because if we go around and we find on the Avenue of the Americas, it's no better, in fact it's even worse. Because what you saw on Park Avenue, there were a couple of new buildings which let the sun through. In this street, there isn't any sun at all, and I think the time at this time was 10:30 in the morning. And 10:30 in the morning, it looks rather bad. You can see the sky is fairly clear. And if we come to Chicago, which is very close to you, it's not any better. We go to the LaSalle Street, and this, I think it took around, I would say 2:30 or 3 in the afternoon. It was a clear day, sun shining, but nothing coming down. That's how dark it looks. And there again, because every building is packed from one end of the block to the other end of the block. And the density is already very high. What we are building today is not necessarily any more dense. What I hope we can do is replace some of these by making taller buildings, but only fill 1/3 the site, or maximum half the site. I'd rather see 1/3 the site. So there'll be a lot of open spaces between buildings instead of just a narrow street in between. Now, this is exactly in some way what has happened. If you look at the plaza that is created at the First National Bank, the First National Bank was about 30 stories or some building right in front of our office. The building you see there, the bluish, that's the Inland Steel building, and that's where we're located right now. This space in front, which is now a big plaza, used to be the old bank building, and it was just filled up from end of the block to the other. Now they've built a new building 60 stories high, but the plaza is actually very pleasant. This is one of the few places people come on a very relaxed, informal basis. Lunchtime, there's always a band going on or some kind of a dancing going on. Few places people come on a very relaxed, informal basis. Lunchtime, there's always a band going on or some kind of a dancing going on, and it's really very interesting. And you can see the kind of crowd we suddenly get, that there's the fountain in the middle, and there's every day, this crowd is not any special occasion. Every day it starts at about 12 and it goes up to about 2 o'clock. There's a function, there's something going on, there's a podium there you can see on the right side bottom, temporary type. There's always some program, either some jazz music or some dancing or some kind of a folk song or whatever. It's always something is happening. And I think it's a great thing that this space could be available. But to get the space available, you have to build a building taller. And the reason is that the tallness of the building is not necessarily adding more area. It is simply making smaller floor area and building the building taller. Now, in the society where economy is still a very important thing, to build a building taller, you must justify and say that I can build for the same price as a short building. And that's where the structural engineering part comes very important, because the part that goes very expensive when the building gets taller is the structural part. And so we have to develop these systems to justify such tall buildings. As you can see also on the Hancock side, we had the same kind of a feeling. We had an apartment and an office building side by side. My partner Bruce Graham said, why can't we put the apartment on top? And we worked it out together, and we said, well, if you think architecturally this is acceptable, we have a system by which we can build a 100-story building for the same price of a 30, 40-story building. And that was, in fact, the critical factor in being able to build a 100-story building. It was not in the imagination of John Hancock Insurance. They were in no need to make a glorious statement or anything. It was really us who really wanted to create an open space, create more environment around, and not sit onto the street with an office and an apartment complex with all the parking structures. Instead of that, we put the whole thing in one building, made the building only about 1/3 the total site, and left the remaining area for the plaza, the reflecting pool, and the rest of the activity. And I think if you go around there at night or in the daytime, you see there's all sorts of people walking around, relaxing, sitting, looking. And I think that is a very interesting thing. But to do that, we have to conceive and come up with a structural system that could be accepted architecturally and expressed, and I'm glad that it could be expressed also architecturally, the base system. So we came up with an idea that we would always build a tall building for the price of a short building. And that means whether the building would be enclosed by a hypothetical glass dome or not, let the building system be such that it costs the same amount. That means if the building is a 30-story or 100-story, the price difference should be negligible. And if we can guarantee that, we can expect a taller building to be built for improving the environment. And I would really have to use that reason. If it didn't improve the environment, I think it would be tragic. But I am on the optimistic side that by doing this, we are opening up spaces in the cities and creating interesting plazas and human space. Now, the Sears building was about the same, it was a structural architectural relationship. The Sears building was another one where the Sears Roebuck, who, as you know, sells very good but economical products, had no interest in going into a very expensive product in terms of a building. They wanted a good economical product, which according to the contractor's initial estimate meant about 50-story building. And then when we came up with this solution of a 110-story building, but a much smaller plan and had this variation, the first question was that we're not interested. We said, how many pounds per square foot do you figure? The contractor, who is a very expert one, said about 32 pounds. So we said, okay, this is a 32 pound. Now are you satisfied? Well, there was no further question. But I think that is the kind of a thing that really makes architecture and engineering work together to create interesting forms and shapes. Not a priori concept, but something that evolves out of this rational ideas mixing together, synthesizing into something that I hope also improves the environment of the urban centers. So Sears, as you know, is an interesting example of that. In fact, all of the buildings, on the left side is the Union Station. We did the composite system the same way, working together, coming up with a solution that made more sense and created a more interesting possible environment. Well, this is, I think most of you probably know Sears. It's a very interesting building, It's the first building and the only building, in fact, of that height or that kind of a range, over 50 stories, that is deliberately built eccentric. It is all eccentric and everything is stable because the structural system that we devised is inherently very stable. All we took is 9 tubes and kept on dropping tubes as we went up, and it did not upset the stability of the building. And yet, in any other traditional form, one could not think of such a tall building built eccentric. The building would kind of lean. Although this building also leans a little bit, we don't tell anyone. Because of the dropping of the tubes, it moves about 2.5 inches. But even the contractor doesn't know whether it moved. He can't even measure it, so it's okay. Now, what it does is that, as you can see, this kind of a concept brings in as I say, possibly a new vocabulary in massing of a tall building in the future. Because suddenly, buildings don't have to look rectangular or uniform section. They could have different volumes, different masses, and still be efficient and economical. So that the shapes and forms can be all kinds of combinations, and yet it would be stable and economical. So that's a very important, interesting offshoot from our study of the Sears building. Now, Hancock, as you know, is again the same kind of a solution where we put everything. As you know, the lower floors, some offices, then the parking from 6th to 13th floor, then 13th to 44th is office, then the swimming pool and the plaza and all that for the apartment. Then we go the apartment up to 94, then the 96 is observatory, then mechanical, then the studio, and there's the restaurant. It's really a very interesting combination of all the functions that otherwise we would have to put sprawling all over the site and ruining the free space. This way, you put everything in one building, and the building base was only 1/3 the total area of the site. Otherwise, we would have a filled up site like any other building. One Shell Plaza building, which I showed before, was also an interesting example. Because of that, we could build a much smaller plan and go up to 52-story. And we also devised an interesting thing to float the whole building in mud. And it's really floating. It's not floating away, it's just floating. And the idea is to simply balance the foundation. Take so much soil out and put the building in so they weigh the same, so nothing happens. Obviously, as you realize, things are a little more complicated than that. Then, as we develop into forms or structural forms, we find its flexibility, its potential beyond the normal forms, and we find suddenly with a tube concept we can mold it in different shapes, like intersecting octagonals or unequal shapes, and yet it's completely stable and it's economical. Therefore, we realize that technology does not necessarily tie your hand. Once you understand it, it in fact opens up a whole new vocabulary in each case. And that is in fact the exciting part of, I think, architecture-engineering interaction. As you see in this project going up in Boston, which is a very interesting shape, yet it's a very efficient economic structural system that's incorporated into the architecture. Now, I wanted to show this because it was a very interesting thing. One time it occurred to me, why do we put all these transfer girders always on the second floor of a building? Like, all the columns comes down and stops. If we look at the old bearing wall building, we see their arch form. So I really wanted to look at it mathematically, purely. How does the load come down if we didn't have a transfer girder? And then proportion the columns and the beam just for those loads and see how it works. Now, we tried that on one building. Now, there again, you must realize the architect and engineer had to work together to accept these solutions. And so we tried on this two-shell plaza. It was kind of a first try where we took the load, and you see without a transfer girder, the load is simply seeping into these major columns in the lower floor. And there's no deep transfer girder. And you can see the tree effect because the load is being caught by those columns gradually. But I think even more clear expression, almost a classical bearing wall kind of expression, was achieved in this building here. You can almost read the arch just by proportioning the columns and the beams as the load comes down, purely on a technical mathematical way. We came up with a very interesting expression which really became an architectural expression. And yet it is a straightforward technological solution of the concept of letting the load flow from the closely spaced columns slowly into the largely spaced columns on the ground floor. So this is the kind of an interaction, the kind of the communication that goes on in Skidmore, Owings and Merrill in the works that we're doing, which makes life very interesting. We are going farther and farther away from starting off with an a priori concept and closer to always starting with a clean slate and looking at the problem and coming up with a solution that is kind of a combined synthesis of both the architectural needs and the structural possibilities. Of course, one has to do model tests, and out of model tests sometimes strange shapes come out. This you don't see too well. But from the model test, you might find that the form of the column may have to be bent a little bit, and we do bend those things. And we always find there's an interesting new form comes out of it. Here, for instance, in the Sears, we ran a wind tunnel test. And we said, we're very open-minded. If this massing of the tubes is too sensitive to wind blowing on it, we'll put another kind of massing. Whatever is more efficient probably would have an interesting reason or interesting look to it. So we tried all kinds of solutions. We tried adding extra masses here, there, and running through the wind tunnel test and seeing whether it vibrates more or less. And we finally came up with the present shape, which really has the most efficient aerodynamic stability. And interestingly, one probably still thinks as a layman, you look at the building and says, oh, what, an architectural proportion and all that, which is really true. But at the same time, that was also the most efficient aerodynamic form that we tested. The others that we tested had higher aerodynamic response. And we do the same. People, you go to Chicago and you look at the Picasso, Chicago, and you think, it's a great sculpture. But you don't know the background of this structural test that goes in. We ran wind tunnel tests and we ran all kinds of things. And the design is in fact somewhat changed. And Picasso signed the drawing because, we have to keep it up somehow. And we didn't want the sculpture to fly away. So we had a series of wind tunnel tests, and out of the wind tunnel, certain minor modifications were made. You would never know what those modifications are because they still look like a product of Picasso. And yet there were few changes that had to be made to make it work. Well, then we talk about environment, and again, structure, architecture works together. And here in Wichita, Fourth Financial, we're trying to find an environment. It's a hot climate, and we wanted to create a 10-story kind of a lobby. But structural stability required that we probably would have to build pylons. So we built these 15 feet by 15 feet square pylons, turned them diagonally, and then used remaining glass enclosure, and used all of these pylons for stairs, mechanical and other facilities, so that they're all enclosures, and yet they create the modules of the overall building plan. Well, as you can see, in the last 12, 15 years, we have done a lot of interesting research in tall buildings, and in fact, from the third on up to the last one, they're all developed because the architects and the engineers worked very closely, because everything was immediately discussed and something came out of it, that they were not just fantasies. And it's the same happened in the steel structure. From the second one up all the way, we have developed and used in buildings all of these systems that are now considered standard for tall buildings. As you see an interesting example here, the belt truss, Milwaukee. There the structure again had its own interesting form. This is not a decoration, this is an interesting way of stabilizing the structure. And we expressed it architecturally because we thought it has the same kind of a strength as the structure itself has. And you can see this building we did not build, but we were trying an idea of stiffening an effect of a diagonal in a concrete building. And we came up with this kind of a concept, and maybe someday we'll use that in one of the buildings. We got to think a few years ahead all the time. Now, even in masonry, some of the things we have to do is do research. In masonry, we're thinking of not this kind of a building, which we did not design or build, but using other possible forms so that we may go very tall if it has to be in different materials. So here is a project that was sponsored by the Masonry Block Institute, and we came up with a series of building forms and shapes that are as high as 50 stories high with plain masonry blocks. But each material, interestingly, will have its own form. You should not design a masonry building that looks like a steel building, or a concrete building that looks like a masonry, or either way. Each material has its interesting potential forms, and we should exploit those forms. This is just a close-up view of these forms of these buildings. This is a masonry 50-story building model, of course. This is the future of the ultimate high-rise, which is a kind of a funny name I gave, but really, how tall can we get? Everybody asked that question. And if someday the society needs really a tall building, I don't think it will need it for the immediate. We can even come up with some interesting solutions like that, where large spaces for playgrounds and such spaces will be available. Let's see. There are other forms that could develop. There again, structural concept would have to relate to architectural forms, as you can see here. As you can see, these wavy shapes of the future that can develop into large apartment complexes. Now, as I said, so far I've been talking about structure-architecture relationship. Now I would like to show you sometimes what a good structural engineer can do when an architectural solution has been reached. Now in this case, actually, the habitat was a very interesting solution architecturally. And in fact, structurally, unless it was solved very right, it would have probably collapsed. But I'm very happy to see that Commandant, who is a really top engineer, came to the rescue and solved the problem. But if you really analyze it and put yourself up on the roof and think where your weight, your load is going to go down to the ground, how it's going to travel, you'll have a little difficulty in finding out which way it's going. And that's what I meant, that the simplicity of the structure requires that you can almost visualize how the loads are flowing down into the ground eventually. And this is another very interesting example of the Opera House in Sydney, which I've visited a number of times, and every time it really flabbergasts me, I should use that term, because this was, again, an a priori concept in architecture. It is a great, beautiful form, but with a very slight modification, it could have been also a rational structure. It was conceived as a shell structure, and the forms that were sketched were impossible to follow any shell theory. So shell can only, according to its, can act according to theory. And since it didn't, the engineers of Arab had to build it by a series of arches and then tie back the arches one after another to make them look like a shell. So the building that was estimated $8 million is today something slightly over $80 million. But I think in American economy, I think we could not afford it. I think Australians supported it by the bingo. So it works all right. Now, we also go into strange places and find strange things where the structure and architecture have interesting relationship. This is the French embassy in Warsaw. Now, I don't know why French had to prove that much, but as you can see here, the canopy in the office entrance had to be hung from way up somewhere, and it's a very, honestly, very tortuous kind of a canopy. And the solution that was achieved was truly, I would say, an a priori thing that was given to an engineer and said, look, make it work, however you have to hang it, hang it. And the engineer, of course, did his best and hung it. And of course, a structural engineer does not have his life always very easy. He goes out, like I did one time on John Hancock, and found this beam. Now, if we didn't find it, probably get buried in concrete somewhere. But we found it, which caused a lot of tragic mood, as you can see. And it did get resolved at the end. So, as a concluding remark, I would say the future of our cities, the urban centers, and this includes the more and more we're getting industrialized and urbanized, even the small towns are looking like cities. The future of the cities, I think to some extent, depends very much how well architecturally we resolve them, planning-wise, sociologically, and at the end, economically. And to do that, I think the structural engineer must work very closely with the architect, just as much the architect must work very closely with the structural engineer. And that's the way we hope we're working at SOM. Thank you. Rather long. Do we have time for questions? Any interests? No, the mechanical engineering is, as you know, is a very important part. In fact, I could talk, almost give a separate talk on it. It's becoming almost like 30-40% of the total cost of the building. But we haven't yet truly incorporated mechanical as a part of architecture. I'd very much like to see, we're trying our best to express the building both internally and externally in some form from the mechanical point of view. Now, in some of the buildings, the mechanical floor is quite nicely expressed, but I think we still have a much longer way to go than we have come with the structural engineering part of it. Well, the research parts that I showed are all done at IIT because that's where I teach. And what I try to do is work with the graduate students. And if I have an interesting idea, it's always possible to find one or two students interested in that concept. And then he can work on his master's thesis incorporating that concept. So we have a pre-thinking sometimes. Many of these ideas, in fact, are pre-thought a year or two earlier on some research project like that. Like the masonry one I was showing you, the masonry people, their grant is given to IIT, and I'm advising the students to develop these schemes. What about questions from there? Well, I think I think the buildings really should not be that close. I mean, this is one of the questions I have. I personally think that in the urban situation, tall building, if we put too many side by side, they're going to have almost the same problem. And I would like to see that maybe the one way to stay within the economic free enterprise system is to zone it according to 4 block units. So that if you build a tall building on one block, the other 3 blocks are actually selling their floor area ratio to you, and then you won't be able to build that tall building in the next 3 blocks. Then again, the other 4 blocks could have a zone. Now this is hypothesis and my personal pet idea, but I really think that one shouldn't build tall buildings side by side because theoretically you might make the density of the city untenable. And I think at some point, from a political, sociological point of view, we have to decide what is the limit of density we'll put as a limit of density for our cities. Because right now, the average floor area ratio or plot ratio of Chicago downtown is only like average, including old buildings, is like 10 or plus minus. Now, if we're going to build new zoning which allows to build 20, 25, which is all right to build 1-2 buildings, but if we're going to build every block, then the average plot ratio will go up to 20, which would be completely untenable for the transportation system, for everything else. So I think this is the kind of a thing that the planning end of it, the sociological end of it, and at the end, it's the political end of it that must consider. As you know, the decisions are not made by the architects or planners. They're really made by the politicians, the city council, which makes the decision. City council can any time decide that the plot area ratio of any building from now on will not exceed 8. You know, they could do it. So I'm against building another tall building next to, First National. Well, the height limitation right now seems to me easily we can build, about 150 stories, really no problem. I think more problem is the limitation of the environment and limitation of vertical transportation. And in terms of vertical transportation, I would think we have to start rethinking. Now, if we're really going to build a 150-story, one has to have a real solid reason to build it that tall. And if you then build it, then I would say we have to restructure our vertical transportation system. We have gone one step, as you know, we're building the double-decker elevators. We might have to go 4-decker elevators with 4 lobbies at big transfer point. I don't know. But I think the height limitation certainly is not as structural anymore. It's more other factors. But I think the height limitation certainly is not as structural anymore. It's more other factors. Yeah, well, the horizontal access between tall buildings is certainly a possibility, but I think in some way, this may be a slightly prejudice on my part. In some way, it truly cuts out whatever sense of clarity you finally develop in the cities. You know, it's like the overhead wires, the cable cars, all the cables hanging all over, and you look up and you see all these connections going on. It might be a problem. Second, of course, is that when you have that, and as you know, a tall building moves. Now, when they're not connected, you don't know that they're moving because you only know moving when you feel it. You can't measure it. You can't measure it against something. But if you connect it, you have a large possible movement going the other way, and it could be quite a serious detail problem. Well, actually, I'm a little surprised. If somebody says architects can build anything, it really sounded like the ad of the traditional engineer rather than an architect, because it's the engineer generally who had, as I said, by training, had the idea of solving anything. The architect was supposed to have more social conscience and senses and not say that. But in fact, interestingly, now I see both the Civil Engineering Society and I think the architectural associations are also saying that they're quite concerned about the social problems and environment. So I think that ad must have been a bad ad. Well, obviously, in the complexity of our society and complexity of the demands put by people in terms of environment, the demands put in terms of the fast construction, fast design, creates a very serious problem in having a very small office. A small architectural office simply cannot handle those problems because just doesn't have the manpower. So in some way, it's an interesting thing. The larger offices, which have the total service, end up getting those projects. Used to be that, you know, Frank Lloyd Wright with few people could get major projects, but now with 6, 7 people, you are not going to get a Sears building or a John Hancock building or any of the major projects because the demand put on is a different kind. Where Frank Lloyd Wright could push the owner around, it's very hard to push an owner around these days. And if the owner says he wants it within 4 or 5 months, a design, you simply cannot do it with 4 or 5 people. You need a couple of hundred people. So there is a distinction that's developing that large architectural offices end up doing large projects, and small architectural offices end up doing small projects. And large architectural offices, interestingly, at least the possibility is that they can also produce more rational projects because the in-house capability of all the disciplines, whereas a small architectural office has to depend on their own judgment what a good structure is, what a good mechanical is, and then have a consultant. But by that time, decisions have been already made, and generally it's hard to change. So this is an interesting development in the last few years. Well, the education of the architect, I think, is, as I said, should have this is my feeling, that should have a stronger social education, but not necessarily the negative aspect of the social education, but the social education in terms of what can be done and not what is always wrong. And I think it's always very nice to relate both, question what is wrong, and immediately try to answer what could be done on a positive basis. And I think also a deeper appreciation of the potentials of the technology and the disciplines, you know. Okay, now the answer is really very simple. As I said, we quite often blame the architect engineer for something that is a political economic decision. That decision comes from the city hall, the city council, which says your plot is 100,000 square feet and you have only built 1 million square feet. But according to our new zoning law, you can build suddenly 3 million square feet. Now there is not a single, in this free enterprise system, that's an economic system, there's not a single investor or owner who will sit around with an old building with 1 million square feet when he can very well immediately build a 3 million square feet building and get that much income. Therefore, he would then hire an architect engineer to design that 3 million square feet building. And this is in fact something that is unfortunately overlooked. And an average man looks at architects, engineers, and blames the whole thing. Now, I think architects, engineers certainly can try to get involved in the city, which we try our best to change planning and all that. But I think it's what is more important is that if the problem is given, or if that political decision is made, then the architect engineer should try to make the best environment they still can make out of that thing. You know, I think that's the best we can do. I wish that there would be broader, deeper political involvement in city planning. And right now, city planning is pure politics and not really deep involvement. Well, it's the same way. It's the same way when you go around and see the ads on gasoline, and you find out the gas companies advertising. They say, please drive your car a little slower. They don't tell you to buy a smaller car. They only tell you to drive your car a little slower so that you can keep on buying the biggest car in the market you can. And the problem, of course, is that the profit structure, which is the base of this society, we have to accept it. The profit structure will try to maximize the profit. Therefore, to really cut that down, it has to come from really a political base. It will not come from nice articles. It will come from people reacting, which is exactly what happened in San Francisco. There came to a point where really people reacted and they slapped down. They really didn't slap it down, but it made it so difficult now that it's hard to build taller buildings in that area. And I think that is a very valid way to do things. And, you know, in Chicago area, we have tried a series of master plans to reduce the density and increase just increase the open space. But when when a developer has a land that has potential buildable area of 3 million square feet, he's not going to listen to good judgment and all that. First of all, he wants his 3 million square feet so he can get the maximum profit. It's, you know, I really don't blame him, because after all, that's a part of the system. So it has to be changed on a political level. It cannot be changed by nice architectural articles. You know, it really has to. Now, I think the young architects probably have a tremendous advantage. They could infiltrate the political structure and you know, generate that kind of a thing, and maybe vote the whole thing back, which would be a good thing. You know, bring back some moderation. Now, like in Chicago, we have the SOM worked on a whole redevelopment of the South Side. I have no idea when or how it will be implemented, but at least the politics, meaning Mayor Daley, is all behind it now. And if it really works, maybe that would be a positive thing, that it would be a planned area development instead of individual developers trying to maximize their profit. It's the same in Hong Kong. I was there, and land is selling for $2,500 per square foot. That's how they're selling. So what can you do if the guy has to buy a land for $2,500 per square foot? He has to build the maximum to make some kind of a profit out of it. So it's a very different. Well. Okay. Plastic by the definition is plastic, and that's really one of the biggest problem of plastic. We have, as you know, we have tried to reinforce it with fiberglass. It makes it a little better, but then it has the problem of, first of all, the fire. It has a toxic problem which has not been totally resolved. And in spite of the fiberglass, it still has a high creep characteristic, the plasticity. And in a tall building, imagine the building slowly goes like that, and it can't do that. It's going to last for 100 years at least. So, well, thank you very much.